Bismillahirrahmanirrahim. Uh, First of all, introduce myself. My name is Engineer Dr.Raja Assistant Professor, Electrical Engineering Department, NAD University. I have done my Bachelor's of Engineering in Electrical from NAD in the year 1998, and then my Master's of Engineering Electrical from same university, that is NAD, in the year 2006, and finally Doctor of Philosophy, Electrical Engineering from University Technology, Malaysia in 2019. And this one is my Google profile. If you want to see my publications, my research areas, you may find my Google profile in the given link. So for the circuit analysis, the textbook is suggested by my co-teacher, Dr. Beenish Sultana, Engineering Circuit Analysis by William Hyde, 8th edition. This one is your textbook and already shared by my co-teacher, Dr. Beenish, on Google Drive. Then reference books, Fundamentals of Electric Circuits by Charles Alexander, Introduction to Electric Circuits by Richard Dorff, Electric Circuits by Nilsson James, Concepts in Electric Circuits by Dr. Wasim Nasim, Electric Circuits by Bogart, Electric Circuits by Alex, or any other book with the title Electric Circuits. You may refer. You can use as your reference book. No problem. The topics covered by me as earlier my co-teacher Dr. Beenish already told you, that polyphase circuits, magnetically coupled circuits, and two-port networks. I will cover these three topics. Let's start from our first topic, that is polyphase circuits. In polyphase circuits, we cover different topics, that is balanced three-phase voltages, balanced Y-Y connection, balanced Y-delta connection, balanced delta-delta connection, balanced delta-Y connection, power in balanced power system, unbalanced three-phase system. So the learning outcomes of this topic, that is polyphase circuits, is you become familiar with the three-phase system, and you know the basic generation from alternator, that how generator generates three-phase, and the basic difference between a balanced and unbalanced three-phase system. And to analyze three-phase circuits and connection pattern of three-phase circuit, that is the three-phase may be connected in a star or may be connected in delta. So let's start from the generation, AC generation. What is AC? AC means alternating current, and alternating current have some frequency actually. That is, it alternates at some value. It starts from some reference value, that is 0. Then it attains its maximum value. Then it comes back to 0 again. Then it starts in negative and goes to maximum, and then comes to 0 again. So it's a cycle actually, frequency cycle, that is 50 hertz. So the AC generation, we need three basic parameters, that are magnetic field, conductor, and relative motion. What happens actually, conductor cut the lines of magnetic flux at some angle. A voltage is induced in the conductor. This is Faraday law of electromagnetic induction. Recall your basic knowledge how electricity generates actually. You need two things. You need conductor, that means which conducts electricity, and you need magnetic field. These two things, and you need the third one is relative motion, that is some relative motion between conductor and in magnetic field. So that relative motion produce an induced voltage inside the conductor. So we must know what is one phase, what is three phase. first of all, we know what is phase. Actually, a live wire is called a phase. Live wire means a wire which has some supply inside. Supply means voltage, right? So live wire is called a phase, and if it is a one phase, that the supply will be the voltage appears between line to neutral is called a phase voltage. Actually, it's a definition of phase voltage. The voltage which appears between line to neutral, and you see the star connection. This is a star connection, and this one is neutral. So in a star connection, these three are lines actually. Line 1, line 2, line 3. So the voltage appears between line and neutral is phase voltage, and the value is 215 to 240 volts. The permissible limit for single phase voltage is 180 volts. That is, this is the last value. Below 180 is dangerous, because our devices are operated at certain rated values. If you give the voltage to below the rated values, the device is damaged actually. So need to give the recommended value to the single phase. Similarly, three phase means the voltage appear between any two lines. For example, line 1 and line 2, or line 3 or line 1, or line 3 or line 1. Between any two lines is a line to line voltage, and its values starts from 415 to 440 volts. And the permissible limit, that is last limit, is 380 volts. Below 380 volts, it's not recommended to operate your appliances. It's harmful. It affects the torques of the motors. It affects the windings of the motor. So this is the last permissible limit. Okay. Now we discuss how the phase generation means single phase. We start from single phase, and we turn from single phase we go towards the three phase. Single phase voltage, how is the sinusoidal wave generated actually. In this figure you see this is a coil which rotates inside the north and south pole of magnetic field. This coil means conductor, and these carbon brushes is to collect the current from the conductors. So this coil rotates, and such then its rotation starts from some reference value, that is 0 to 360. So when it rotates and it starts rotations, it starts from some reference value, and when it is at reference value, the magnetic lines and the conductor have 0-degree phase angle, 0-degree cutting angle. So there is no voltage induced in the coil. As such, as coil starts to move, there is certain angle formed between magnetic field and conductor, and when that angle formed, it produces an induced voltage inside the coil, and that voltage is in terms of time, because it's sinusoidal, it is instantaneous value. It is voltage maximum cosine of omega t. Let's see, this one is a first figure in which the conductor is at reference position. So the conductor and the magnetic field are parallel to each other, and we know that in parallel the angle is 0. So no voltage is induced inside the conductor. In fact, it is present in between north and south, north and south magnetic field. But because magnetic field and conductors are in parallel, no angle forms between conductor and magnetic field, so voltage induces 0. Now in this figure you see your conductor moves actually, and it moves from reference value to some value, that is, let's say 45 degree. So it's moved from reference value to 45 degree. Now it forms an angle with the magnetic field, and it voltage is induced inside the conductor, but that voltage induces not maximum, it is 70% of the maximum actually. This one is 70% of the maximum value. It's not maximum actually. When it is maximum, see the next slide. Now see this slide. When conductors come exactly perpendicular to magnetic flux lines, that is maximum voltage induced in the conductor, and see the waveform, it attains peak over here, maximum value, because angle is maximum, that is 90 degree between magnetic flux lines and conductor. Now this conductor further moves to 45 degree, and now this value of induced voltage is again 70% of the maximum value. And when the conductors come to means its rotation is 180 degree, that is it starts from reference value, it moves to 45 degree, then it moves to 90 degree, then it's further moved to 45 degree, and finally to 180 degree, that is 180 degree. And now in this condition the conductor comes in parallel with the magnetic lines, and we know the angle between magnetic lines and conductor is 0, so the voltage, no voltage is induced, and the voltage is 0 at that instant. Now in this figure the conductor moves from 180 further 180 to 45 degrees, but here you see the conductor with whose polarity changes actually. Before, this conductor was in the influence, for example the dot, it was under the influence of north pole before, and the cross, it was influenced under the north pole. Now it switches actually. The conductor which influenced under south pole now comes in the influence of north pole, and the conductor under the influence of north pole now comes under the influence of south pole. So the polarity is changes. See the waveforms. The waveform is now going towards a negative, because the negative voltage is induced because conductor switches the position. The conductor switches position from north to south, south to north. But the value is 70% of the maximum, because angle forms 45 degree. Now in this figure, the conductor moves, and conductor comes in perpendicular to the magnetic field lines, but it switches actually. See, this one was under the influence of south pole before, now it is under influence of under north pole, and this conductor was under the influence of north pole, now it is under the influence of south pole. So it switches actually, the conductor switch the position, and that's why its voltage induced is also switches, and it becomes negative maximum. Why maximum? Because it forms a 90-degree angle between magnetic flux lines and conductor. Now the same situation again, the conductor comes to 45, further moves to 45 degree, the negative 70% value of the maximum, and finally the conductor's complete cycle, that is 360 degrees. So in this we see the sinusoidal wave is formed actually. It starts from some reference value, then it attains a maximum value, then it attains a zero value, then it attains a negative maximum value, and finally it attains a zero value. Somehow this cycle is continuous actually. As soon as conductor moves, the sinusoidal cycles completes. So that's uh, that's how we get the sinusoidal voltage from a AC generation. Now we learned that how we get the sinusoidal voltage waveform. Similarly, we learned that a single phase generation. Now move towards three-phase generation. In three-phase generation, before single phase, it was only one conductor that's move around the magnetic field and produces sinusoidal wave of its own. Now we see we have three conductors, that is three-phase generations. Three conductors, you can see conductor 1, conductor 2, and conductor 3. Three conductors that moves across a magnetic field and forms three-phase sinusoidal voltages of same magnitude and same frequency, but they are displaced from each other 120 phase difference. Physically, these conductors are placed 120 degree apart from each other. We can see some advantages and importance of a three-phase system. In three-phase system, we save copper material and it is more efficient, and it's transmit the same power of amount, and its cost less, its weight also less, so the structure on the poles also bearable. And three-phase motors are larger. Actually, three-phase, the advantage, main advantage of three-phase, it fulfills all the needs. It fulfills the needs of residential consumer. It fulfills the needs of homes and offices, that is domestic, residential, commercial, and industrial. So three phase is enough for it fulfill all the requirements of all the single phase and three phase. Because in three phase you can take either you want two phase or single phase, you can take from three phase, right? But if you go for single phase, you need more conductors, and it is not cheap, it is not economical. You have more losses, and you can see the first three-phase electrical system was patented in 1882 by John. Okay, this one is an overview of a distribution system that looks like you have a power substation, you have a transformer, you have a transmission line, and you have a power plant, right? Where you transmit your electricity, you generate electricity, you transmit electricity, and finally you distribute the electricity. Remember, the generation is three phase, the transmission is three phase, and the distribution is three phase. Here is another way out as a layout. You can see generation, transmission, and distribution. This one is power generation. And after actually we have generation limits. We can generate electricity from 11 kV to 33 kV. These are generation limits. Sorry, 11 to 22 kV. And then it is stepped up by power transformer for transmission purposes. The electricity generates in a limit, and then it transmits to a higher voltage, that is 132 and 220 and 500 and 345. There are certain transmission voltages. So it step up through power transformer and it transmits. After transmission, it goes to a substation for step down transformer for distribution purpose. It step downs to a value 11 kV, and then it goes to a distribution transformer finally, and further step downs to 400 and 220 volts. This is another layout in which it is clear that you can see you have a generation, uh, and you have a transmission. These are transmission lines. You have a power transformer. You have a power, this one is power station. Power transformer step ups the generation to a transmission voltage. Then distribution transformer, it distributes the electricity. It step down the transmission voltage to a distribution voltage. And what is distribution voltage? Distribution voltage is three phase and single phase. Three phase is 400 volts and single phase is 220 volts. See, it give to the residential consumers. Now we can see our three static coils rotating magnetic field. Our rotor, that is rotating part of the machine. Rotor rotates. Rotor is hierarchy of conductors. Inside there are conductors which are rotates physically at 360 degree. Start from some zero reference value. And we have a stator. It is also a hierarchy of conductors. A stationary part of the machine. So rotor rotates inside the magnetic field produced by stator, and when rotor rotates, all conductors cuts that magnetic field, and the voltages are induced inside the conductors. If the number of conductors increases, that is, we have three-phase system and they are 120 degree apart from each other, 120 degree, 120 degree. So each phase produces of its own waveform, that is magnetic, that is sinusoidal waveform. It has certain maximum value, it has certain zero value, it has certain in between, that is 70% of the maximum, what you say. Three phase generation. We see three phase generation. The rotor rotates inside the stator, and three phase are actually three separate windings or coils. Coils and windings are same thing, right? So they are physically 120-degree apart from each other, and the rotor rotates inside that magnetic field and cut the magnetic field lines and produces voltages, induced voltages. Now you can see this the waveforms of all three phases: phase 1, phase 2, and phase 3. See, each phase produces of its own sinusoidal wave. Either it's induced voltage or induced current, same waveform. See, phase 2 lags phase 1 by 120-degree because phase 2 is 120-degree apart, so it lags. What it means lags means it is behind phase. Means when phase 1 attains its maximum value, phase 2 was it starts actually. So it lags 120-degree. Phase 2 leads phase 3 by 120, and so on. See, and phase you can also see say phase 3, phase 1 leads to phase 3 by 240-degree, vice versa, right? If the phase 1 is reference, so with reference to phase 1, the phase 1 leads to phase 1 by 240-degree. Uh, you're well aware of these the words legs and leads. Means legs means behind and leads means apart, away. Now we move towards the three-phase connections, as I've told earlier also. That the three-phase connections, we have possible combinations are star and delta. And this is some transformation you have already learned in your course, Basic Electrical Engineering, BEE, delta Y transformation and Y delta transformation. So if you see the impedance, that is transformation impedance of Y connected system is equals to delta connected impedance divided by 3. Means delta impedance is 3 times value as Y connected impedance. So balance three-phase voltages. Now we have to understand the term balanced. Balance means we have a impedance at all the phases which have the same value actually. Same value means, for example, the impedance connected at phase 1 has a value, for example, 2 plus J2 ohms. At phase 2, 2 plus J2 ohms. At phase 3, 2 plus J2 ohms. That means impedance same. What is impedance? Impedance is a position in the current flow of AC. So if the impedance is same, the current being same. So if the current is same in all the phases, the system is balanced actually. What is a practical example of the balanced system? Is three-phase motors actually, because the three-phase motor windings have all the phases same reactance value because it is manufactured by the same vendor, same coil dia, same resistance, same reactance. So phases are actually the three-phase motor is a perfect balanced load example. What is unbalanced? Unbalanced is single phase load actually on your distribution transformer. Take an example of your home. Your home, the load is not balanced. Why? Because the fan, the tube light, the refrigerator, the air condition, all have different amperes because their impedances are different. So this is unbalanced, right? Now come towards the phase sequence. What is phase sequence? Actually, Phase sequence depends upon the direction of the rotation. That is, you know how electricity generates, as I talked earlier. When rotor rotates in a certain magnetic field, it generates electricity. But the rotation of the rotor is also very important. Either the rotor rotates in a clockwise direction or it rotates in anti-clockwise direction. Whatever the direction being of the rotor, against that direction of the rotor, we got certain phase sequence. We have a positive phase sequence, we call it ABC, and we have a negative phase sequence we call ACB. So in a positive phase sequence, our voltage, that is the second phase voltage, lags the first voltage by 120, and in negative phase sequence, it vice versa, that is, it reverse actually. That's the voltage, the second voltage, it leads the first voltage by 120 degree. So phase sequence depends on the direction of the rotation. So it was the phase sequence generated against the direction of rotation. So what is phase, what is line? You see in this figure, it's very clear. The voltage appear between any line to neutral is a phase voltage, and the voltage appear between any two lines, either line 1, line 2, line 3, but in this case we have only two lines, two phase, two wire system. So it must be clear to you that what is phase voltage, what is line voltage. As I have talked earlier, that is balanced and unbalanced three-phase system. This is an example you may see. The unbalanced, we have impedances that are different. That is 4 plus J2, 6 plus J3. See, the values of impedance are different. I have given the example also. Like your homes, in your homes, actually in single phase load, the loads are not balanced. Why? Because single phase loads have different values, because every appliances have certain impedance, and that impedance not matches actually. But but in a motor, three-phase motor, all the three phases are manufactured by one vendor, and that is balanced actually. The reactance of all the three coils, the reactance, the impedance of the three coils are same actually. So motor is a balanced load, and single phase domestic, commercial, residential are unbalanced. That's why we use neutral. We need neutral for that. And what is the purpose of neutral wire? The purpose of neutral wire is to return the current. Actually, it flows from the line and it comes back to the neutral. Neutral gives the return path to the current actually. You know, current will flow in the mesh actually. When loop completes, the current will flow. When the loop incomplete or disconnect, then the current will not flow. So the neutral is to complete the circuit actually. So let's move to three-phase generator. These are the vector diagram, as we discussed earlier. All three phases are 120 degree apart from each other. Phase A is 120 degree apart from phase B, and phase B is 120 degree apart from phase, and phase C is 240 apart from phase A. So in a balanced system, all the phase voltages, that is EAN, EBN, ECN, equals to 0 in a balanced system. This is single phase 2-wire and 3-wire circuits. We can see if we have a single phase, then we have single phase 2-wire system. Single phase 3-wire system, we have a neutral also. So and that's why we prefer three phase 4-wire system. Three phases, three lines, and for fourth wire is the neutral. And the advantage of the big advantage three phase, you can either take any phase or phase to phase from three phase. This is three phase 4-wire system. You can see phase 1, phase 2, means phase A, phase B, phase C, and we have a neutral, and we have a waveform of all three phases, phase A, phase B, phase C. And every phase attains its sinusoidal waveform in a fashion. It gains its maximum value, it's 0, then negative maximum, then again 0. Sinusoids. In this, you can see the expression for the current. There is omega t minus of theta. You know, actually our load, all the machines are inductive in nature. They have coils actually. Coils are inductive in nature. So inductance, due to inductive nature, the current lags the voltage by some angle. That's why in current equation you see the angle appears, that is minus theta. In voltage equation, it doesn't see any theta, any angle. It is first voltage taken as a reference, so 0 degree. Then second voltage is 120 degree apart, minus 120. The third voltage is minus 240 as compared to first voltage. The currents are like this. The first current, the phase A current, lags the phase A voltage by angle theta. Similarly, the phase B current lags some angle theta from phase B voltage. Similarly, phase C current lags phase C current. Phase C current lags phase C voltage by the angle theta. And the instantaneous power, instantaneous means changes actually with respect to time. Actually, in sinusoidal quantities, we have values of voltage and current which changes its magnitude with respect to time. Every time it changes its magnitude. So instantaneous value, there is time t. See, t involved. Instantaneous values. Power is a product of voltage and current. That's why the instantaneous power is nothing but the product of voltage into current. And because it is three phase, so all the three phases, phase A voltage and phase A current, phase B voltage, phase B current, phase C voltage and phase C current. So phase, you can see value, that is RMS value. RMS means root mean squared value, effective value. Also, we can say effective value. What is RMS value? Root mean squared value. Actually, sinusoidal wave, we have a variable values of voltages and current. Variable, that means it changes with time at every instant. Instantaneous. As I said earlier, it changes the value, either voltage, either current. It changes this value with respect to time. Every time it changes the value. So root mean squared, or a DC component, that is fixed value of an AC waveform. It is RMS value. We must know that the voltage values which are recorded by instruments, that is multimeter or ammeter or whatsoever, they are giving you RMS values actually. The 220 volts is also RMS value, right? So RMS values of voltage and current are measured by all the instruments. So three-phase generation, another diagram for the three-phase generation. You can see there are three coils which are 120 degree apart from each other. Coil A, coil B, and coil C. All these coils are 120 degree apart from each other, and every coil generates its own value, induced voltage value, that is sinusoids at 50 hertz, phase A, phase B, phase C. So when phase A attains its maximum value at that time, phase B attains some negative value. And also note that phase B, it starts from 120 degree. See, when phase A starts from 0 reference value, then phase B starts from 120. After 120, phase B starts, and after 240, phase C starts. See, phase C starts after 240. So how that's how they attain their different values of their maximum, minimum, zero, negative maximum, minimum, and zero again. So that's how we obtain all three-phase sinusoidal waveforms. So as we talked earlier, we have different connections of three-phase coils. It may be connected in Y, that is a star pattern, and it may be connected in delta. Now we are discussing a star connected generator. See, all star connected means all three windings have a common point, that is neutral. It forms a Y connected or star connected. And in a star connection, the voltage between line and neutral is phase, and the voltage appear between any two lines is line voltage, and the load is connected across this three-phase 4Y system. Now you can see in star connection, the line current equals phase current. See, the current flow through phase is equals to current flow through line, the current being same. This is the property of a star connection. The current of line and phase are equal. See, the current from line and phase are equal. But the current between the voltage of the line is equals to root 3 times of the phase voltage. See, this voltage is bigger. This voltage, that is line voltage is greater than phase voltage. That is, it is under root 3 times of phase voltage. Line voltage is greater of magnitude in star connection, and it is under root 3 times the phase voltage. Normally, the star connection is preferred where in the auto transformer. Actually, auto transformer means one winding transformer. So star connections, the windings of the auto transformers are usually in star pattern. In a star pattern, we have, if you see vice versa, that is phase voltage is divided. If you under root 3 line voltage, if you divide it by under root 3, you get the phase voltage. Phase voltage is reduced actually. In terms of auto transformer, we prefer actually star connection, and the big advantage of a star connection is the neutral point. Actually, we need neutral at distribution side, as I've talked earlier. That we need to drive the single phase load, which is line and neutral. So the biggest advantage of star connection is the neutral actually. So our distribution transformers are the secondary side of our distribution transformers are also star pattern connected. Their primaries are delta connected and their secondaries are star connected. The distribution transformer, it steps down from 11 kV, that is 11,000 volts, to 400 volts phase to phase, and 220 volts from phase to neutral. So all distribution transformers are star connected. Their secondaries are star connected because star we have neutral, so we can fed the load single phase and we can fed the load three phase. So when we fed the single phase load, we need line and neutral, and when we want to fed the three phase load, we need all three lines to fed three phase loads. Thank you.